So what is a prehash and what has it to do with post-quantum signatures? The cybersecurity world is changing, and where the signature methods of the past, such as RSA, ECDSA and EDDSA, are likely to be replaced by FIPS 204, otherwise known as MLDSA, Module Lattice Based Digital Signature Standard, or dilithium, and FIPS 205, otherwise known as SLH-DSA, or Stateless Hash-Based Digital Signature Standard, or Sphinx Plus. As part of the standard, we define the key generation process, the signing process, the verification process, and the pre-hashing process. So what's a pre-hash? In MLDSA, we can create a pre-hash of a message and then use this to create a digital signature. Normally, with a digital signature, Bob will take a message M and then pass it with his private key SK to a signature method and produce sig is equal to sign SK, M. And where we pass the message to the signature method, and which will then take a hash of the message and produce the signature. But what if the message is large and we are using a limited processing device? Well, for this, we could perform the hashing outside the signature method and thus perform a pre-hashing process and pass the pre-hash to the signature method, such as sig is equal to sign sk, h, that's the hash of m. And where the message value passed will be much smaller than the large message value. This will help with the buffering requirements for the signature method, and where we will typically only require 32 bytes or 256 bits for a hash, or 64 bytes for our 512-bit hash. These days, a typical hash is produced by SHAKE256, and where we output a 512-bit or 64-byte hash value. With SHAKE256, we have an XOF function, and where we can create any length of hash. Normally for a pre-hash, this is 512 bits. Pre-hashing reduces the burden on the signer. The great advantage of a pre-hash is that we can use a powerful CPU to generate the pre-hash and then pass it on to a limited processing device, such as with a smart card. It is unlikely that the smart card will have a great deal of memory to buffer a large message. In this case, the smart card has a private key stored, and then where a powerful CPU generates a pre-hash and then passes this onto the smart card, and which then returns back a signature based on the pre-hash, the signing method, and the private key. Supporting other cryptographic hashing methods in the signature. Another advantage of using a pre-hash is that we might want to use a new cryptographic method that is not supported by the signature method. For example, we might want to use Blake2B for our signature. For this, we can create a Blake2B pre-hash and pass that into the signature method. Overcoming forgery attacks. One problem of this method is that we need to make sure that the verification process knows about the pre-hash and where the pre-hash needs to be created before the verification process. This can lead to a forgery attack. Luckily, this can be overcome using a domain separation. With this, we add a context CTX, and then where the pre-hash is computed with hash is equal to the h is equal to the hash of m, such as using SHAKE256 with a 512-bit output, and then the signature will be sign 0 concatenated with the OID, that's the object identifier of SHAKE256 with a 512-bit output, concatenated with CTX, and concatenated with H. In this case, we identify SHAKE256 with a 512-bit output with its OID in the message passed to the signature production. The normal signature would then just be sign, open brackets 1, concatenated with CTX, concatenated with M. The method of using OID and the PreHash is actually defined in MLDSA, and we can see this from the specification. Thank you.